Hi guys, and welcome in this new video tutorial of Blender and Geometry Nodes. In this video I want to show you how to make a full laser system. You will be able to control the emission source like an origin point or elements of a mesh, the emission, chaotic or following a curve shape, the spreading in 2D and in 3D, rotations, bounces, animations and other features, so let's get started. I'm working with Blender version 4.5.0, but this can work also for the new version 5.0. And to start with this tutorial, we can press Shift-A, Mesh, Plane, go in the plus button, go to General and Geometry Nodes. Press New to create a new workflow and enable the Snap tool here. Okay, so the idea behind the laser and the emission of the beams is very easy and simple. We can start with one vertex. We can choose a direction of the emission, for example, the Z direction. Next, we are going to extrude this vertex, and then following this direction, we are going to ask if it can hit a particular surface of a collection of objects, and if there will be a hit, we are going to take this extruded vertex and we are going to replace it on the position on the surface. Otherwise, if it doesn't hit anything in the space, we are going to replace the position of this extruded vertex on a particular distance we are going to define inside our parameters of the modifier. This will be the first iteration, and we are going to repeat this process again and again, recalculating from this point the new direction based by the reflection of the previous direction of the extruded vertex, that is this, and the normal of the hit surface. So from this direction and this normal, we are going to reflect this vector, and we are going to take the new direction. And next, after this stored information, we are going to extrude again this vertex and ask if it will hit the next surface on the collection. If it is true, we are going to replace the position of this new extruded vertex on that position. Otherwise, we are going to replace the position at a particular distance, always based by our parameters in our workflow, and so on for the number of bounces we are going to define inside our modifier. So we need to make a points node in which we want to create the first vertex, and I'm going to use the point because next we are going to emit more than one ray from the origin point or the elements of a mesh. So we are going to increase this number of count. I leave the position on the origin point of the object, and as you can see in the 3D space, I have this plane placed in a way we can use to have a hit following the Z direction of the extrusion of our vertex. Because we are going to use the extrude operation, we need to have a mesh, so real vertices, and to do this we need to convert these points in a vertex. But before this, I want to store the important information we discussed earlier, that is the vector of the direction of the next extrusion, okay, the emission of the beam. So we can start using the Z direction as a default vector for all the initial rays. Next we can convert these points to vertices, and now we could use directly the extrude mesh node. But before, I want to store two other important informations. One is important to define what is the vertex or the vertices that hit something. So I want to store the information if this is hitting something. This is a Boolean type, and because this is the first vertex, we need to imagine if already hit something because we need to extrude it. So I'm going to set this to true, because we are going to mask and select only the vertex we want to extrude next. And another variable that is very useful, and that is the to extrude. So this means that the vertices hit something, and this is the variable that identifies what are the vertex or the vertices we are going to extrude in the next iteration of the repeat zone we are going to use soon. We also need to set this to 1 because otherwise we can't extrude the vertex. Now we can extrude our mesh. We need to select here the vertices, and we are going to take this vertex and extrude it, but leaving these at the same position of the previous vertex, okay, so without any offset, because we don't know if it hits something now. We need to select from this extrude mesh only the vertices that have the hit to true and also the variable to extrude to true. Only these vertices will be extruded. So in this moment we have two vertices, as you can see here in the spreadsheet, both of them in the position of 0 and both with the direction of z axis as the direction of the extrusion for the emission of the beam, both with the hit and both with the extrude. Why are you seeing the hit and the to extrude and the direction also for the extruded vertices? Because Blender, when you apply a particular operation on some elements that already have stored attribute, it inherits all this information on the new elements created. So in this case, we already had the true value in the hit and to extrude Boolean variables of the first vertex, and we obviously have this information also for the new vertex created. For this reason, it's important to reset these informations, so we need to identify the true vertices to extrude or to move along the direction of the emission. So we don't need to use both of these two vertices, but only the last extruded vertex. We could use the top selection here, but I decided to use another way to identify the real last vertices of these meshes. So imagine you have for example, a mesh like this, and you have a point here for the emission and another point here for the emission. We have an array that goes here and array that goes here. We have a surface and we have a reflection. We have a reflection here, and we also have another point here that hits nothing, so is here, the last point. As you can see, we have a first reflection here and nothing then. Here we have a first reflection, a second reflection, and then nothing. Here we don't have any reflection. So in this case, the number of the indexes made by Blender using the extrusion is this. Imagine you have 0, 1, and 2 in the starting point of the workflow. Next, we extrude these vertices to go to the right direction for each vertex. And as you can see, we can have an indexing like this, 3, 4, and 5. Next, we have another extrusion, but only for these two vertices, because here we don't have any hit, and we have the number of 6 and 7. And next we have another extrusion with the 8th. Now, the identification of the last point of this bunch of lines is not simple, because we have 0, 3, and 6, and next we have 2 and 5, and here we have 1, 4, 7, 8. So this is not an optimal sorting of elements inside this group. So to easily identify the last vertex of this group of edges, we can easily convert this mesh to curves, and this is a very perfect way because Blender starts a new indexing of the curves based by the starting number of each group of elements. So as you can see here, we have 0, 1, and 2. So for each curve, it starts with the lower number of the index inside the same group of elements. For this, the lower number is 0, so the curve will start from here. The same for this bunch of edges. So as you can see, the lower number is 1, so the next curve will start from here and the next will start from here. Saying that, we can easily identify the last point for each curve using and masking them using the end point selection node. This is a particular selection mask that sets a value of true or false starting from the beginning of the curve or the end and going back from the end of the curve. So for us, it's important to identify the last point of each curve, and next we can store this information inside what? Inside the two extrude variables and save this information in the value. In this way, we are going to have here false, false, and true. False, 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 and true. False and true here. In this way, for each iteration, we can always select the last vertex. I said vertex, so from here we need to convert again this curve to a mesh like this. Now, if I press Shift, Ctrl and click, oh, I forgot to set here the boolean, you can see we have only two vertices starting from the origin point that are here, and we have only the last point with the true value. So we can recap a little bit. This is the extrude last hits. This is a new frame with F, set the last points to extrude. Now we need to reset the heating because we don't know if the two extrude vertex or vertices will hit something. So we need to store again the information of the heating, selecting the V hit and setting here the value of false for both. Now we can duplicate these and set true only the vertices that already have the two extrude to true. So we can use the name attribute and select here the to extrude, select only these, and now the tricky part. So the value here is not true always because we need to identify and check if it is something. And to do this, we can use this colliders collection we already have here in the group input. As you can see, I added a new attribute as a collection. So we can add the new group input here. We can select our colliders here in the modifier. We can link this to a collection info to get the information of this collection and realize the meshes of this collection, because otherwise here we have instances and we can't use the raycast node on instances but only on real mesh. Now we need to move this a little bit and we need to link this hit here. The raycast node, that is the node we can use to ask if something is hitting something going in a particular direction. The target geometry is the group of the surfaces of our collection. For the source position, we could use the position itself of the vertex, so we can use this link, and the ray direction. The ray direction is stored in the variable called V direction, so this direction here, and we can recall it adding the name attribute, choosing here the V direction, and the ray length we can set a very high number like 10 millions meters. And now, as you can see, we have a heating here. So if I decrease this in 0.1 meter, we don't have any heat because the end of the emission ends here in this point. So I need to set a very high number to be able to heat the surface. And now that we have the heat value, we can add the set position node to replace the position of these to extrude vertices, where on the heat position, and if I do this, you can see we have the correct position of the new extruded vertex. Now, what if I don't have any heat? So if I press this pin and select this surface and move this surface away, you can see the new position of the vertex is 0, 0, and 0, so it remains in the same position, and we don't want this. We want to replace this position with a particular distance along the direction of the emission. So for this reason, we can add a new float value as the ray length. This is a distance from 0, and this structure is single. We can set, for example, 0.2 meters. And now we need to ask if we have the heat or not. So in this heat, I'm going to add a switch, changing this type in a vector. And if we have the hit, we want the hit position. Otherwise, we want to have a different position based by what? Based by the previous vertex position. So not the position of the vertex itself, but the position of the previous extruded vertex. And you can ask me why the previous? Because in the next iteration, if I don't take the previous position of the vertex, so not the last extruded vertex, I would replace the same last extruded vertex, adding this ray length on the same distance based by the previous iteration of the loop. I explain. If I have a vertex here and the next vertex I move this 0.2 here and I apply the entire workflow in the repeat zone for the rest of the iteration, again I would take the last extruded vertex and I would replace its position based by the actual position plus again 0.2 meters, and I don't want this behavior. I want to take always the last and move it in the space starting from the previous vertex position, adding the 0.2 meter set here. And again and again and again for each iteration, because for each iteration we identify the last point of each curve as the vertices we need to extrude. So each time I repeat the operation along the reflection of the other beams, in this case, in this group of vertices, this will be always the last point of this curve. And I would always try to reposition this point in the space. So on each iteration, I will know that this point will not hit anything, and I will need to replace the position of this last extruded vertex, always based by the previous vertex position plus this set of ray length. So to do this, I need to take what? The position, but evaluated in a different index. So evaluate at index minus 1, so the previous index of the same curve or group of edges. And it's very convenient to use this subtract 1 because transforming the mesh in a curve and then in a mesh, we have a perfect sorting of indexes inside each group of edges, and it's very important. So for example, for this group of vertices, we will have an index of 0 and next 1, okay, plus 1 in this direction. And for this, we will have, for example, 2 and 3 and 4 and 5. So for this vertex, the previous will be always this vertex and not this or this or this or the first of all vertices. And here we will have always 0.2 meters or whatever set here. Now that we have this position, we need to add what? The length, but in what direction? The direction stored inside the same point. So we can use the direction scaled by the group input value of the ray length and add this vector to the actual position of the previous vertex and link these in the false condition. Now we can link the output of this switch inside the position, and you can see this extrusion, okay? So I set 0.2, but I meant 2 meters, and as you can see, I can increase or decrease this ray length as I want. But if I take the surface and I move the surface here, we have the heating. Now we can take all this information and move this a little bit, and we can create some frame. So this is the get position of the previous point. This is get the new position, if not hit. And for this bunch of nodes, we can press F and set hit the surface or move in the right position. Now, before the repeat operation, we need to calculate the new direction for the next extrusion. Okay, do you remember this point here? We have the hit all to true and to extrude all to true, and we store the information of the direction. Now we need to override this information of the direction, and to do this we need a new store name information, setting here the new direction based by what? The previous direction, So we needed to take the previous direction. We needed to filter only the to extrude node used here, okay, for the set position, because for these vertices we needed to rewrite the new direction for the next extrusion. So we can select only these, and we can calculate the vector of the new direction based by the previous direction, reflecting this on what? On the normal, the heating normal of the surface. But keep in mind this: if I link the heat normal from this raycast directly here and next here, we have an issue, because the last extruded vertex on which we are overriding the new direction is already placed in the new position in the space. So now the position is not here, but is here on the surface itself. So after this set position, the store name attribute recalculates all the previous workflow of the raycast based by the collection of objects and the position and the direction. And this position now, for this source position of this raycast, is no longer the previous position, so here, but is the new position here, okay? Because we passed through this set position. So before this set position, the position of the last extruded vertex is here, but after this set position, the position vector of the last extruded vertex is here. So in this exact point, we are not able to calculate the correct raycast operation and the heat normal and the heat position, okay, because we are already on the surface itself. So we need to capture the information of the heat normal before the set position to be able to transfer this information for the same index and the same vertices from before the set position to after this set position. To do this, we need to move a little bit this set position and add a capture attribute here in the middle and link this heat normal here and use this heat normal inside this reflect. In this way, we are making this operation. We go inside the store attribute and we save the heat information. And now here we have the information of what vertices are heating something. Next, here we are capturing or saving in a cache, okay, for each point, so each vertex, we are saving the information of the heat normal before replacing the position of the last extruded vertex. In this way, when the vertex is still here, we already know the normal and we can use this normal to calculate the future direction for the next extrusion of this last extruded vertex. Next, after this capture, we have the set position that calculates from the beginning the correct position from this switch based by this raycast node and starting from the source position of the extruded vertex. So this position, and this position is this point, not this point. Okay? This is very, very important. In this way, this direction is this, the captured normal is this, so the reflected vector is this, okay, like a mirror. And now we are saving this information inside the direction vector of what? Of the last extruded vertices, so this final vertex. Now we can have a new frame here and store the new direction for the next iteration. Iteration, why? Because we are going to take all these group of frames and use a bunch of time based by a new input node here called bounces, that is an integer number starting from 0 and is a single type. We can add a repeat zone. We can go here and link the geometry inside and this geometry here. We can take this last part of the repeat zone, placing it at the end of the workflow, linking this to the geometry and this in the group output. Now, what we need is to set the correct number of iteration, and for this we can add the group input, link not the bounces itself, but bounces adding 1, because if I don't want any bounce or next reflection, we just need one emission, okay, through the space, based by this ray length. So if I set 0 here, I want at least one execution of all these workflow to have this piece of extrusion. So I can add 1 here and link this to the iteration. Now I can delete my annotation and increase to 1 my bounces, and as you can see we have the correct reflection of the ray, and if I increase or decrease this ray length we have the correct replacing of the last extruded vertex that doesn't hit anything, and you can see it by this false value, and we can replace this last extruded vertex where we want in the space by this ray length. We can select these two nodes, press F and set initial states. Now we can add other surfaces, so we can duplicate these and rotate in this way, move these here, and you can see the heating, okay? The heating like this. I can select this and increase another time. Now there's only one last thing to do inside this workflow that is absolutely super important. Take a look. If I rotate this object a little bit, watch what happens. I rotate this and you can see this particular strange behavior. Okay, the correct reflecting of the line sometimes and sometimes not, or you can see also no reflection at all inside this particular environment. Why does this happen? Because if I zoom in this point, we have here the last extruded vertex. Okay, everyone agree with that, but there is a problem. In this point, we have a point that we need to extrude another time to be able to go in this direction. But if you take a vertex and place it here in this point and you want to pretend to emit a ray from this point, okay, the new position in the next iteration, to the next surface, you can't, because this point is exactly on this surface. So this is a problem I discussed in a previous video. I'll put here and in the description of this video tutorial. If you have a point already on the surface, you need to move a little bit out from the surface itself, a little bit in the new direction before taking this new position as the source position for the heat. Otherwise, the system can get the same position of the vertex as the new position of the heat, because you are using the same surfaces of the collection and no other objects. So if in the previous iteration you have a heating on a surface and you move the vertex on that position of the surface, you need to move a little bit out to make a new ray beam from this ray cast. You need to choose a new source position to emit the new beam. And for this reason, we can't use exactly the position of the vertex itself, also in the case where the initial position is in the origin point, but we need to take the position, add something based by what? Based by the direction, it's obvious, but scaled by a very little number, okay, like this, 0.001 or even less. In this way, as you can see, all works because we are moving the vertex from this position a little bit out to avoid the heating on the same surface where it is in this moment, and take this position as the source position for the ray cast and use the ray direction for the next emission. This is very, very important. So remember, if you move something on a surface where this element hits, if you need to recalculate the new position for the new heating, move a little bit out this position. So add a little piece of the direction useful for the emission. Now what we can do is to take these nodes here, press Alt-P to go out from this frame, press F and set fix already heating of previous point. Now the repeat zone is finished. And now if I take this object and I continuously rotate this in the space, you can see the correct reflection of the beams. Now we can easily transform these in a mesh using a particular technique, a little trick, because if I take these and convert to mesh, you can easily see this particular problem, curve to mesh. We don't have a mesh, so we need to convert this mesh to a curve here like this, and we can use an arc as a primitive and use this for the profile. But as you remember, we have the problem of the radius based by the angle of the segment of the curve. So to fix this problem, you can use my even radius group node. I leave here in the video or in the description of the video, or you can use a different kind of trick to avoid this behavior, and this is very simple. So the idea is to split the edges of this mesh, and I will leave this mesh to curve for a reason we are going to discuss next. So I'm going to convert this curve to a mesh at a time, and I link this to split the edges and link this in a mesh to curve another time and link this here. And now as you can see, we have all the splitted edges, and for this reason the transformation from a curve to a mesh is correct, because we have a separated edges or piece of curve. So we have multiple curves here. Now we can export the radius of this arc and increase the sweep angle, and we can export also the radius. Why this arc instead of circle? So to avoid the problem of the UV map of these pieces of curve, if you want to use the shader, etc., you can use my video here to avoid this problem, or you can easily replace the circle with the arc. Otherwise you could have some issues in the making of the UV map, the correct UV map of these pieces of curves. We can add some panels here, one for the mesh, and this is a toggle attribute. We can rename this in ray radius. We can insert this here, the resolution, and we can also add the new input for the material if you want, like this. We can also save the spline parameter factor and capture this factor before the curve to mesh to store the information of the path of the curve and the profile, and in this way we can link these in a combined XYZ and link this in the X and this in the Y, and store the information inside a new 2D vector called UV map, like this, and link this to the vector, and we are making the UV map of the mesh. There are some videos of my channel that describes this way to save this information. We can set the material like this, linking a new duplication of the group input and linking the material inside, and link a new switch to decide if we want or not the mesh. So we can link the mesh in the switch, and if we want the mesh, we can link this output of the geometry in the true condition. Otherwise, before the split edge, we can move this a little bit down and link the output of this curve to mesh directly in the false condition, and link this in the group output. In this way I can enable or disable this mesh and set a different number of parameters, like this. I will take all these nodes, press F and set light even radius technique, because the real even radius technique is in my other video. We can add another attribute here called emit to emit something from this object if we want. So this is a Boolean operation, structure type single. We can duplicate this switch another time, duplicate the group input and link the emit. So link this in the true condition and false otherwise. In this way I can emit or not the entire group of beams. Now, because we are going to add another feature, that is the emission from not the origin point, but the elements of a mesh, we can duplicate this Boolean attribute in show source if we want to maintain the original mesh of the geometry on which we emit the lasers. So we can duplicate this switch another time, we can duplicate this group input, and we can join the output of the laser with the original geometry and link this to the true condition. Otherwise we only want to have the laser system and link this to the geometry, and we need to link the show source like this. Now, as you can see, we only have the laser system. If I check this, we also have the plane, but we are going to move this down at the end of this list of parameters. Now, a last thing about the animation and trimming feature. So as you can see, I added here a mesh to curve for a reason, because I want to add a new panel here for an animation. So I can add a new panel, call it animation, and this is a toggled panel, call it animation. And inside this animation, I want to add two parameters. One is a factor, and this is a parameter from 0 to 1, and the subtype is a factor, structure type to single, and I want to add another attribute as the length, because I want to use this distance for the trimming of the curves based by this laser system. And this is very cool if you want to make an animation of the making of these lasers through a room or whatever environment you want. So in this way, we need a menu switch, because we need to decide the type of the trimming. We can go in the node and replace this in vector, and this is length. We can drag this in the group input directly, go in the group, rename this in type, and we can take this type and go here inside the animation. The default is a factor. It's good. Structure type to single, and now we can link this output in the curve and add the trim curve like this 2 times, link the same curve here and here, choose for one the factor, and link from the group input what the factor values inside the end and the length inside the end based by the length of the curve, and link the output of the factor in the factor menu and the length in the length. In this way, as you can see, I can increase this factor from 0 to 1 to have the right behavior, or I can use the length instead. The result is the same as the factor for one only ray, but you will see for multiple rays the result is very cool. So we can move this a little bit. We can select all these nodes, press F and animate these, or you can set trimming if you want. We can take this type and click expanded to be able to select these in a more cool way inside the modifier. And now we are done this. Now let's make multiple rays. So as you can see, we have only one point and we store the direction, but if I want to have more points, initially I reset the rotation of the plane to be able to see the direction only on the z-axis. I hide for a moment the source, and I want to move the colliders here below the bounces. Why? Because above the colliders I want to define all the information about the rays. Now let's play with the direction of the new rays. We started with these values, so we can add a vector constant in the z-axis like this, and we need to do something here in the middle before going from here to here. So to make a new group inside, I can press Shift and right drag, select this reroute and press Ctrl G. And as you can see, I have now a group I exit from this group, I scale this a little bit, and I want to call it laser directions. So now, as you can see, the starting direction is the z-axis in 1 point. I want to increase this number based by the number of the rays, and to do this we need to add another attribute here that is integer number from 0, structure type to single, and I can call it rays count. I can add the group input and link the rays count inside this point like this. And now for each point I'm saving the same information of the vector, but I want to spread these vectors in 2D and also in 3D. So to spread something in 2D, you can easily imagine this. You have 2 rays or 3, and we want to use the plane y and z to be able to spread in all these direction the rays. So I want to have a ray here, a ray here, a ray here, a ray here, and so on. So in 3D you can see this particular behavior, but to have this behavior we need to use an axis of rotation. And as you can see from this perspective, we can see the x-axis and we can use this axis. So if I take this axis as the axis of rotation, we can imagine this rotation and rotate each of these rays around this axis, starting from 0, okay, so leaving the z-axis as the correct initial vector, and starting the rotation on this part or the other part with a range from a positive to a negative value of angles, covering the entire space in 2D. Okay, so to do this we need to go inside this laser direction group node, and we need to take the actual vector of the rays. We can call it normal, the normal of the vector, and I'm using the normal name because next we are going to use this on the normal of the elements of a mesh, so this is perfect. So we need to rotate this vector using a particular axis. In this case, we don't need to worry about the center of the rotation, even if we are rotating something in the 3D space from a mesh. Why? Because we are rotating something that is only the direction of the extrusion of something, and the direction is always a vector starting from the point 0, okay, the origin point of the object. We can absolutely use the center of the origin point to change the direction from a starting normal and go in another direction. So we can leave this center at 0 and choose the axis. As I said before, we can use this axis, but there is a problem. The x-axis, as you can see here, is working now because the normal is perpendicular to this axis. But if we have the direction of the starting normal not exactly in the z direction, but starting from the normal of a face that is not pointing on the z direction, how can we find the right x, relative x of this new z-axis, so this new normal of the face of this mesh? We need a way to find this perpendicular vector. So to find a specific perpendicular vector, you can use this technique. Imagine you have a vector like this, and for this we want to have this axis of rotation. But if I have this rotation, I want to have this axis of rotation. So to do this we can use a specific and defined standard axis based by a vector, in this case the y-axis, doesn't mind, and in this way we can use a particular mathematical and geometric function called cross product. So if we use the cross product, and I leave here the video to explain what is the cross product in detail, we can get from this vector and this vector a new vector perpendicular to the plane of the two first vectors. So this is the plane between these two vectors. Okay, I have a new vector in this direction or in the other direction based by the order of the two elements inside the formula. If you invert the order of these two vectors, you can get a direction or the opposite direction of the new vector. At the same time, for this vector here, the plane is this plane here. okay, between this vector and this vector. So the perpendicular will be this direction, so a rotated direction. This means that you cannot have a particular decision based by the source vector you want to use to calculate the new perpendicular vector. You only need to decide a specific vector in the space and use the cross product. The only case you need to keep in mind is if the source vector is the exact vector and has the same direction of the same vector you choose to calculate the cross product. So if you have two parallel vectors, the result of the product is 0. So it's the only case you need to change the axis to calculate the cross product in the workflow. So in our case, we have multiple rays and we need to calculate this axis of rotation, so this perpendicular. So to calculate this perpendicular, we need to use, for example, the y-axis. So in this way, we can take the normal and calculate the cross product using what? The y-axis. And in this way, we can take the normal and use this as the new axis, and we can change the angle. And I can prove you, because if I set here the factor and go to 1, deselect the mesh for a moment, set one ray for the emission, you can see the correct surface. Now, this is the axis we used in the cross product to calculate this axis of rotation. And this means that now if I increase the angle, you can see we are moving and rotating the axis around the x-axis. If I increase the number of the rays, all these rays are rotating around the x-axis. But if I want to have a randomized effect, I need to link this angle to a random value between a range. So I can add an attribute here called spread 2D in degrees, and I can convert this in radians. I can link this to a multiply to have a random value from minus the value of the radians and plus the value of the radians. So I can link this in a random value minimum and this value of the radians as the maximum. So I can have a range between a minimum and maximum for the spreading. In this way, the up vector will be inside this range of angle of rotation, and I can link this in the angle. Now, if I go out from this and increase this spread, you can see this particular behavior. And if I go to 90 degrees, you can see I have a range between minus 90 degrees and plus 90 degrees. And if I increase the number of the rays, you can see this particular spreading, okay, from nothing to a maximum value like this. And if I increase again, I can go to the other part. So as you can see, the limit is 180 degrees, and we need this information out in this modifier to be able to control this spreading. So we can export this spread in the group input, but before this we can go inside and define the limit from 0 to a number of degrees using the angle here between 0 and 180 degrees with a default of 90, structure type single, and we can go out. We can link these in the group input, and not only this, we can use, instead of angle, we can use the factor to have a better visualization of the numbers with a default of 90. In this way, we can increase or decrease the value from 0 to a maximum of 180 degrees. Not only this, we can also rotate these rays along the z-axis, so the normal itself, to be able to see these also in the entire plane x and y, so in 3D. So to take this range and distribute in 3D, okay, in three-dimensional space. We can enter in these laser directions, repeat this process, so duplicate this vector rotate, and I can duplicate these nodes based by a new value inside this group node that is the equivalent spread 3D in degrees. If I link this in the angle, all works, but I need to link the correct axis of rotation. And now the correct axis of rotation is the normal itself. So the z-axis in this particular case, or the normal of the element on the mesh. I can take this spread 3D and change this in angle. Default 0 from 0 to 90 degrees. We can expand this group node, link this in the group input, take this, change this in a factor, like this from 0 to 90, and now I can use this perfect slider to increase from 0 to 90 the value of the degrees. Now, two things. One, as you can see, we have a strange behavior rotating the Z. Why? Because inside the laser directions group node, you can see this random value. Now, the random value is based by the initial ID of the element, so this ID is the same and the same seed for this random value and for this random value. So if I increase or decrease the spreading in 2D, I'm using a particular random value that is the same random value also for the spreading along the z-axis. This means that the same range on a plane is the same range of values used for the other plane in the other direction, and this will create this particular result. So to see better this strange behavior, I'm going to move a little bit this surface here. I select this and I delete the annotation. As you can see, the vectors that are rotated by a little value on the x-axis, so the 2D spreading, are also rotated by the same little angle around the z-axis, and you can see they are near the original position, whereas the vectors that are rotated with a very big number around the x-axis, and you can find them here, are using the same random big number, also rotating along the z-axis. And this is why the rotated vectors here, if I increase the 3D, are also rotated with the very big number in this direction, or in the opposite direction if the value is negative. So to avoid this parallelism of behavior, we need to change one of these two seeds to have a different random values for each vector. Indeed, if I set one or another seed number inside this random for this rotation in 3D space, you can see we have a different value of random angle for each vector along the rotation on the z-axis. And this is the behavior we want. So now if I decrease these, and we can see a better result from the top, you can see we have all the vectors distributed here. And now if I increase this spreading, you can see the distribution along the 3D space. Now the second part, why 90 degrees as the limit? Because from the top you can see we have all the vectors distributed on this line. So if we want to have a spreading in this direction, or this direction, or this direction, or this direction, as you can see, we only have a range from minus 90 degrees here to plus 90 degrees here, or if the vector is in this side, we have minus 90 degrees or plus 90 degrees if we are working with the clockwise method. And this is why the maximum range of this slider is from 0 to 90 degrees. In this way we can distribute these vectors in all the 3D space, because if I increase this to 180 degrees and then 90 degrees in this way, we have a sphere of emission, a random emission in all the direction of the 3D space. Now, as I said before, we have only one issue if we have the vector of the ray in the exact direction of the positive y-axis for the rotation, because the cross product between y and y is equal to 0. Because I remember you, the cross product is the multiplication of the a vector by the b vector and sin of the alpha between these two vectors. So sin of the alpha is a periodic function that gives us a value of 0 at 0 degrees or 180 degrees, okay? So when the two vectors are parallel in the same or the opposite direction. So to avoid this issue, we need to ask if the normal is equal exactly to the y-axis. If this is false, we can use the y direction as we used until now, and we can link this here in the cross product, linking the normal as the first vector. If we have the normal equal to the y, so in the true condition here, we can switch using the x-axis. It doesn't mind. In this way, we can control this particular and limit case. And now the spreading is done. We can exit from this, and we can also add another rotation we want to manage for our purpose, always based by the normal input. Always inside, we can duplicate another time the vector rotate, and we can duplicate another time the group input and link this angle out in this group input using the normal as the axis of rotation. This is a very basic rotation for all the vectors together. So in this way, we can rename it in rotation. We can set a structure of structure type single. We can exit from this, and we can link this rotation inside the group input. In this way, we can use this rotation. As you can see here, if I increase, I'm rotating all the vectors of the rays. We can select all these nodes, press F, and call it origin emission. We can move these new attributes a little bit above, like this. Now, as you can see, if I move these near the surface, we have the correct laser effect and reflections. I can increase or decrease the number of the rays, I can rotate these, and we can get the correct behavior, regardless of the rotation of the object. We can increase the number of the bounces, so in some cases we can have multiple bounces at the same time, like this. If I take this and rotate a little bit, you can see the number of the bounces is increasing, and all works as expected. Now, the last part is to allow us to emit something from elements of a mesh. So we can use the same, all the same part of the workflow, and we only need to add something here in the middle, choosing the source we need. So we can move this origin emission a little bit, adding a menu switch, go in the node, and we can set here origin, points, edges, points or vertices, as you like. Faces, vertices is better. We can link this menu in the group input, and we can call it source, like this, link the in the position, and link the origin output in the origin menu item. Now we need to reset the position of the object. I reset also the rotation, go in edit mode, press A to select all the elements, and X to delete all the vertices, press Ctrl A and add an icosphere. Exit, and now I want to emit something from the vertices of this icosphere. So to do this, what I need is to take the group input node and ask me how many vertices that are inside our geometry, so I can link this to a domain, and this is a mesh, it's correct, and I need the point counts because I want to multiply this point count by the number of the rays, because I want to have for each vertex of the mesh the same amount of rays. So I can link these ray counts and the point counts here, and I can add the points node here and link these in the count. And now I have, if I press Ctrl Shift click and select vertices, you can see here 1600 points. I can link this point in the vertices, and I can decrease a little bit the number of the rays, like 5, for example. Now, the problem here is the position of the points, so I need to change the position of the points not in the origin point, but in the position on the mesh itself. So I need to sample what position, so the vector of the position for each point and take the position and transfer this position for each point on the mesh. So I can link this geometry and take the position based by the index like this, take the index and move this in the position, and as you can see we have the correct positioning of the rays. But there is a problem. Now I have 210 points, but the distribution here is not correct because the number of the vertices on the mesh are less than this number. So if I go here with the mouse, we have only 42 points. This means that from 0 to 41 we have the correct positioning of the points. So for example 0, 1, 2, 3, blah 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 until 41, and from the number 42 to the index 209 all these rays are in the same point as the 41, all in the same position, because I have not enough indexes or not enough vertices on my mesh to sample the position and transfer the position on that point. So what we want is this: take the first 42 elements, so from the index 0 to 41, okay, and distribute this little package of points on the meshes. So 0 on the 0, the 1 on the 1, the 41 on the 41. Next, I want to take the next package from 42 to 83 and redistribute starting again from 0 to 41. So on the vertex with the index 0 on the mesh, we will have the point 0 and the point 42 and the point 84 and so on. On the vertex 1 we will have the index 1, the 43 and the 85 and so on. In this way we can distribute all the points we have here. In this way each vertex of the mesh will contain 5 indices, so 5 future rays. To do this, we need to take the index and use the module operation, linking the point counts like this. So imagine you have a triangle like this with 0, 1 and 2, and we have 5 rays count, so 5 rays for each element. We have 15 points. So if we execute the module from 0 and 3, we have 0. 1 module 3 is equal to 1. 2 module 3 equal to 2. 3 module 3 is equal again to 0. So as you can see, we have this package, this little package with the 0 index here, 1 and 2, and again 3, 4 and 5. 6, 7, 8, 9, 10, 11, 12, 13, 14. As you can see, we have the perfect package of 5 rays for each index and in the correct position. From now, we need to calculate what? The direction, as we did for the origin emission. So easily we can take these 3 nodes, press Shift D to duplicate, press Alt P to go outside the frame, go here and link the output of the position inside this geometry and these in the vertices. But in this case, we are not going to take the standard normal on the Z, because otherwise this is the result if I decrease for a moment all these two spreading, or if I increase a little bit the 2D to see the result. And this is very a bad result because I'm not following the normal on the mesh. So we need to change the normal based by the mesh itself. And to do this, we can use the same technique, duplicating this group of nodes, linking the same geometry, but instead of using the position for the attribute we want to get, we can link the normal, and we can link this normal here. Now this is wrong because I also need to link the point counts in the floor module, and now it's all good. Okay, we are emitting from the vertices of the mesh, and if I increase or decrease the spreading, you can see the correct behavior. If I increase the rays counts, we have a correct behavior on the mesh. Now I can take all these nodes, press F, and set vertices emission. In the same way we can do this operation for the edges. It's very easy to do. We can duplicate the entire workflow, go here, call it edges emission, and we need to change this linking the edge count and change the sample domain in edge here, but not here, because we are storing the information on the points made in the space. We can link this output in the edges of the menu switch, and we can do the same for the faces. So we can duplicate this and link this output in the final part, go inside the name, faces, emission, change the face count, change the domain here and the domain here, leaving the values on the rest of the workflow. Now we can go in the group input and move up the source like this, and we can decide to have the same behavior for the edges, and we can show the original source or choose the faces, and you can see the correct behavior. And if I increase the 3D spreading, you can see the correct spreading in the 3D based by the correct axis we discussed previously. Now, if you want to emit this from a curve, it's simple. Convert the curve in a mesh, and you can use this as an input geometry for this workflow. We can add another part for the faces emission. For example, the distribution. Let's distribute the rays not exactly on the faces of the surface, but in a random position. Okay, so with a random distribution on the surface. So to do this, we can add another menu and we can duplicate this, calling this distribution. And to do this, we can start with the vertices emission, because I'm going to use this as the start. And we can duplicate this part, go here. We can add a menu switch like this, calling the first item on position and random. Now, the first face emission is here on the position, and we can rename this in per face and rename this part in faces emission with random distribution. Now, what we need is to take the group input and distribute points on faces like this, and for this reason we can expose the density in our group input node like this and link the density here in a random way. We need to store the information of the normal inside, so we need to take this normal for each point on the face and save it in a normal variable. Next, we need to transform this output from points to vertices, because we are working with a mesh, and from this part of the vertices we can use the same workflow as before as the vertices. So taking the point counts and multiply this number by the rays counts and distribute the position of the points based by this sampling operation. And at the end, keep in mind this is not correct, so the normal is not this. We have no information of the normal as the attribute itself, because we passed through a distribution of points on faces, but we have the v_normal attribute, so we can call the name attribute and take this v normal, change this in vector, and take this normal instead of that normal attributes. Now we can link directly this in this menu switch. We can add the group input to link the distribution to this menu and link this output in the making of the rays on the faces of the mesh. Now, if I change this position in random, you can see the distribution is randomized on the faces of this mesh, and we can increase or decrease the density, and for this reason we can also move this density up near the distribution, because it needs only for this type of distribution, select the density and change this to single. In this way, if I change on position, the density will disappear. Last part about the emission, and this is very funny, is the emission based by a curve profile. So instead of using the source from the faces, I'm going to use the origin, and I hide the source. And imagine we have this particular surface on which we have the reflection, and this is correct. But now I don't want to have a spreading in 3D in a chaotic way, but I want to use a shape of lasers based by a curve. So if I take and make a curve like a circle, for example, outside the colliders, it's obvious, and I go in the top mode, isolate, press edit, and I subdivide at moment, take these 4 control points. I use the cursor as a pivot and press S to scale. Okay, imagine we want to use this shape for the emitting of the lasers. We can go in the laser system and we can add another menu switch, so a new distribution attribute in our group node. So I can use a menu switch another time. I can duplicate this distribution, but we are going to use this distribution as the menu for this origin emission. So I can add the group input like this and link this second distribution used only in the case of the source origin. We can select the node, go in the node properties and change this to random, that is the standard origin emission, and the curve shape. So we can link this output in the random and link these in the origin. Now we are going to make the part about the emission using the curve profile. So for the curve profile, we need an object, and specifically a curve. So we can add here in the middle a curve as an object. We can select these. Now the number of the ray counts will be used as the resample of the curve itself. Okay, so imagine a number of lines based by the number of the rays using the shape of the curve itself. Okay, so we can reuse the same value. In this way, we can add the group input, we can take the curve, take the object information to get the geometry, leave the original. In this way, I can move my curve where I want in the 3D space, but the laser system will always use the correct information, resetting the position of the curve before applying all the stuff. We can resample the curve based by the ray counts like this. Very easy to do. We can duplicate the group input and use these to make our points count, and we can reduplicate this store name attribute to store the direction and link this result in the curve shape. But now the tricky part, the direction. So imagine we have the origin point here in the 0, 0 and 0 components of the 3D space. Now the direction, the extreme direction for all these control points of the curve, so the points we are making here, should follow the direction of the position of each control point starting from the origin point of the object. If I go in the top view, you can see this shape. So if we start from here and we take, for example, this control point of the curve, you can see the position in the space of this control point has the same direction I would save inside this store name attribute. And the same for this, for example, and the same for this. So the direction is correct, but in an extreme spreading of the rays. Indeed, if you look these vectors, not from the top, you can see we have the maximum spreading from the z-axis. Okay, so the starting direction we saw before in the other part of the tutorial. We need a system to go from this vector here to these vectors here and rotate in a correct way all these vectors from the z-axis to the final and extreme case. First of all, we can take the position and sample the index node, link this curve, take the position for each index and transfer this information inside our direction. And if I link this in the direction of the rays, you can see this behavior. I'm using this Bezier ray count 43, the ray length 0.9, so 1 meter, doesn't matter. So what we need is to have the option to use the spreading to go from the z-axis to the maximum rotation, so this case here. And to do this we need a vector rotate node starting from what? Starting from the vector of the z-axis, so we need to start from this vector for all the rays. Link this in the value. Now if I want to rotate each ray going down to the maximum rotation, I need, as before, a new axis on which the vector needs to rotate. So, for example, for this vector here, I can start from this rotation up, and I need to calculate a new cross product between the final and the initial rotation to get the axis of rotation to get this vector result, starting from the z vector. So if I take the z-axis and then I take the final vector and I calculate the cross product, I can get this vector here. And if you don't remember the result of the cross product, you can easily see the order of the axis in this sphere. So the x as the first vector of the cross product and y as the second vector for the cross product will give us z as the final vector and the direction of the positive z. So in this case we need to rotate the axis because we have these and we have these and we need to get these. So if we rotate and the x is this and the y is this, as you can see from this perspective, we will get the z. So we are going to rotate in this way this vector. So we can take the z-axis and we can calculate the cross product with this final vector and use this as the axis for the rotation. And now what we get is this. If I increase this value, you can see this distribution in the space. I'm trying to show you, and to show you in a good way, I needed to take these two surfaces and move a little bit out, otherwise we can see the result of this spreading. And if I increase this, as you can see, we have this result here. This result is wrong. If I set 90 degrees, so the maximum, you can see the correct direction for each ray, but the wrong emission length. So the distribution in a radial space is correct, but is not correct if I decrease this in this way. And this happens because I'm using the same logic for all the rays, regardless the starting distance between the origin point and the final point on the curve. So to have a correct shape in the space, we need to proportionally rotate more when the control point is far away from the origin point and rotate less where the point is near the origin point. For this reason, the proportion from 0% and 100% needs to be calculated by the maximum length between all the control points of the curve. So the maximum length is from here to here, or from here to here, or from here to here, or from here to here. So we can use the distance between the origin point and the position of the control point itself. So for this reason, we need to take the position of each control point that is on the curve itself. From this, we needed to calculate the length. From the length, we needed to calculate the minimum and maximum using the field min and max that can give us the minimum and the maximum length of all these control points. And now we need to use a map range where the length is the value, so the input that can be big or small. We need to link the maximum in the maximum, and the result of this map range needs to be a range from 0 to 1 as the range of percentage, from 0 to 100. Now we can multiply this value by a number and link this to the angle. In this way, if I have 0 of the value, I have no rotation at all for the control point near the origin point or the point away from the origin point. But if I increase this, you can see a different value of rotation for each point. And as you can see, if I increase the number of the rays, you can see that the points that are near the origin point, so that have a little distance, are rotated less than the control points that have a position far away from the origin point. Do you see it? This point here is more rotated than this point here, because from up, this point here originally stays here near the origin point, is closer to the origin point than this point. So for this reason, this point is rotated more, and you have this beautiful shape of distribution and emission. And in this way, I can increase these to have a finally value of pi divided by 2, and that is this. Okay, you have this particular rotation. As you can see, we have the maximum rotation on these points and less rotation on these points, with a correct proportion from 0 to 1. Now let's link this multiplication to the 3D spread attribute we already have in this group node, and we can add the group input, link the spread 3D in a 2 radiant, and link these here in a multiply. Now, if I increase this spread, I can go from 0 to the maximum of 90 degrees. I can use these, decreasing a little bit the number of the rays, like 50, and I can take my surface, go on the X, and if I go down a little bit, you can see the perfect reflections of the shape on my surface. And I can do beautiful things. I can increase or decrease the spreading and multiply the number of bounces using multiple surfaces, like this. You can rotate the object and all works as expected. Keep in mind you can also rotate the curve because we are using the original object info inside this node. If I use this relative, keep in mind the distortion of the shape because we are rotating it. So if I rotate like this, you can have a very squeezed and stretched shape. This is not a very convenient way to work, so leave the original as is, and in this way you can move or rotate the curve profile where you want. We can select all these nodes, press F, and rename it in distribution from a curve. We can rename it in lasers. We can turn off the pin, select one group input, go in the select group type, press Ctrl H twice. We can move this a little bit to have a better workflow. We can add a material, go in the shading. We can use an emission shader instead of the principal BSDF, change the color and increase the strength, and let's decrease to 30 the number of the rays and enable the mesh. Select the emission material. This is the final result, and you have the lasers to the origin in a random mode, spreading in 2D or in 3D as you want, like this. And the good thing is that you can add, for example, a cube, a very big cube, and play with this object, rotating it inside the cube or whatever shape you need. You can reuse this workflow, transforming it in an asset. Click with the right button on the name and mark as asset, or right click directly on the object and set mark as asset if you want to automatically import also the collections and materials you set in the default file. You can always download this file from my platforms, link in the description. The idea of these lasers starts from a project I made 2 years ago that I want to extend with other features inside, and now I can't say too much about it because it will be a surprise, but the starting point of that project is this. So thank you guys for watching this video. I hope you learned something from it. I hope you will use this project a lot. If you like my work, please subscribe to my channel, check a like, and see you to the next video tutorial. Bye!